Right, let's go to alpha and beta decay. Example of alpha decay is radium changing to radon and then alpha particle. What happened to the A and what happened to the Z? Well, alpha has
Reduced by 4, decreased by 4. Z,
sorry, I think you're a bit
increased
soft,
by 2.
too soft, can't hear you. Uh,
Hello?
why is this so soft? Okay, hopefully you can
Yeah,
hear me.
yeah, I can hear you.
Okay, can hear you now. Many alpha emitter produce alpha particle of only one energy. It's quite monochromatic. Alpha particles are said to be monoenergetic, and they have very nearly equal range in a particular observer. Plus one energy, so the range is quite similar. Right? So if we meet alpha, A decreased by 4, A is the nucleon number. Z, the proton number, decreased by 2. Memorize. And if we look at conservation of, yep, what's the problem?
Nothing. I was sneezing.
Oh, okay. There's radium, right? There's radon. Radon has a mass m and then speed v. Helium has a mass small m, speed v, and together we add them up, becomes your radium. Right? Let's assume that initially has no speed. The conservation of momentum, sum of momentum initially equals sum of momentum finally. So 0, right? Initially 0. If we take this one as positive, then opposite direction will be negative. And we got our mv equals to mv. So we can see that the ratio of the speed of alpha to radon is fixed by the ratio of their masses. Cannot escape. It's fixed by the ratio of the masses. The ratio of speed of alpha and daughter is determined by their masses. So if one go to the downwards, the other will go upwards. Very straightforward. Not like beta. Many alpha emitters produce alpha particles of one energy only. We're just repeating. Alpha particles are said to be monoenergetic, and they have nearly equal range in any particular absorber. I think we are just repeating. Okay, beta decay. Basically, there are two types. One is beta minus, one is beta plus. Beta minus emission will be electron emission. Nucleon number of an electron is 0. And a proton, right? For electron, the nucleon number is 0, and the proton number is -1. Right? Can write it as that. C14 decay to nitrogen, beta minus, and antineutrino. We should be able to write the equation. Right? That's the equation. And we can see that for carbon, N is 14 minus 6 is 8. Whereas for nitrogen, N is 14 minus 7 is 7. A is constant. So we can see that a neutron the neutron decreases from 8 to 7. Z, whereas Z increases from 6 to 7. This is called an antineutrino. The E there shows is electron antineutrino. And there's the electron antineutrino. So you need to remember that A stay constant, Z increases by 1. As for beta minus decay. A neutron converts to a proton. So an alternative way of writing is just to write the neutron converts to a proton. That means this is a neutron as a proton. Beta minus decay. Here a neutron transforms into a proton and an electron. Beta minus and antineutrino are emitted. It's a 3-particle decay, not a 2-particle like alpha. Beta minus are emitted with a continuous spectrum of kinetic energy. So if we look at the kinetic energy, intensity can think of a number of particles per unit area per second. You can see that it's continuous, right? Not one energy or two energy. Neutrino were first proposed to exist more than 20 years before they were directly detected. Wow. How is this so funny? Because we learn from our theory before we can experimentally measure it. Electrons emitted from nucleus have a continuous range of kinetic energy. That's what the graph shows. The emitted neutrino take varying amount of the same total energy released in the decay. So alpha particle is very straightforward. The speed ratio depends on the masses because it's a 2-particle decay. Whereas for 3-particle decay, the neutrino can take some of the energy, different amount of energy, and then the rest will be left to beta. So that's why the beta has different energy, a continuous range of energy. What happened to the nucleus in beta decay? Right? There's an alternative way of writing. A neutron changes to a proton, electron emitted, and then there's a antineutrino. Here, a neutron transforms into a proton and an electron and an antineutrino are emitted. You want to put an E, can put an E there to tell you that it's electron antineutrino. This is for your info. How do we know that? Right? Track made in bubble chamber. Right? There's a 2-particle. One going this way, one going that way. The reason why they curve is this heavier, so it's in the magnetic field. So heavier curve less, beta curve more because it's lighter, and as it loses energy, it curves more and more. This is your A2 work. The curving is due to the deflection in magnetic field. Radius decreases into a spiral as beta minus loses energy traveling through bubble chamber liquid and therefore slows down. Beta cannot be a 2-particle decay. You can see that it's not a 2-particle decay. Not like one will go up, one will go down, or one to go left, one to the right. It shows you that there's one going up, one going sideways, there's another one going somewhere this way. So it's a 3-particle decay. Since 1914, physicists knew that beta minus decay are emitted with a wide spectrum of energy to a maximum. How is it possible? Since the energy associated with decay in the nucleus of that isotope should be the same, all beta particles should have the same energy. It follows that the varying missing amount of energy must be carried off in some other way. Right? With a 2 two particle decay is simple. One will carry part of energy, the other will carry the other part of energy by alpha decay. But this is a three particle decay. So the third particle will carry on the rest of the energy. It can vary from 0 to the maximum value. Okay, let's go to beta particle positron emission. Example, oxygen 15. Right? This is a symbol for positron. 0, 1. The subscript represent a proton number. This is your electron neutrino. This new element has an unchanged mass number. A is constant. Mass number is constant. But atomic number Z, that is decreased by 1. You can see there. From 8 goes to 7. Right? So Z decreases by 1. For beta minus, it's an increase. Your neutron changes to a proton. So here we can see that it is a proton changing to a neutron. Right? Proton changing a neutron. Another way of writing it, proton changing to a neutron, positron, and then electron neutrino. A positron has the same mass as an electron, but opposite charge. Or another way of saying is an antiparticle of electron. Same mass, different charge as well. Opposite charge, not different charge. Opposite charge. Same magnitude. What happened in the nucleus in the beta plus decay? We are just repeating. Right? Proton changing to a neutron and a positron and electron and neutrino. Okay. Okay, there's the symbol for positron. Antiparticle. Positron is antiparticle of electron. An antiparticle has the same mass as its particle. That means positron and electron have the same mass. A particle and its antiparticle has equal but opposite charge. The only difference between a particle and antiparticle is opposite charge. Magnitude the same, but opposite charge. Antiparticle, an unstable particle, and an antiparticle have the same lifetime. Some neutral particle and their antiparticle are identical. Example, photon and meson. Right? That's a symbol for meson. Other neutral particle and antiparticle are not identical. What is a neutrino? Neutrino are one of the fundamental particles which make up the universe. They are also one of the least understood. Neutrinos are similar to the more familiar electron, with one crucial difference. Neutrinos do not carry electric charge. That's the problem with neutrino. Right? It doesn't carry a charge, so we cannot use electric field or magnetic field to study it. Because neutrinos are electrically neutral, they are not affected by electromotive force which act on electron. Right? Whereas electron, we can use magnetic field, we can use electric field to study it. Right? Electromagnetic force cannot detect using electric and magnetic field. Neutrinos are affected only by weak subatomic force of much shorter range than electromagnetism, and are therefore able to pass through great distances in matter without being affected by it. If neutrinos have mass, they also interact gravitationally with other massive particles, but gravity is far weakest of all the four known forces. Okay, what this is saying is that neutrino, if it has mass, the mass is very small. It passes through literally matter. It has no charge. So that's why it's not that easy to detect neutrino. And since the mass is very small, gravitational force is also very small. That's the symbol for, right? It's like a V lah, but it's a Greek alphabet lah. It's a Greek alphabet. Neutral, rest mass. Today they have found that it has a mass, very small. Predicted in 1931, observed in 1956. Each fission releases floods of antineutrino. That's a symbol for antineutrino. Interact only weakly with matter. That's the problem because interact weakly with
Sure.
matter. We cannot use it to detect matter anything.
Is there a V or a U?
This one is like a V lah. It's a Greek
Uh,
alphabet. Greek alphabet. Occasionally will be on head-on collision between neutrino and proton, producing a positron. Right? When there's a head-on collision between a neutrino and proton, producing a positron. Okay, we won't bother about that. Right? You don't need to memorize decay series. Know that it does exist. Right? That means it's unstable. Urium-235 unstable. It will keep on decaying until it reach lead, which is a stable isotope. Background radiation, natural radioactive isotopes provide most of the background radiation. 37 from radon and thoron gases in houses. 19% gamma rays from rocks and soil on Earth. 17% from radioactive element in body. Just memorize 2 or 3 lah. The others are 14% from cosmic ray. Medical, mainly X-ray, would be 11.5. Fallout, nuclear waste and industry for nuclear testing lah, 1.5 lah. So the first four, right? Natural one is about 87% lah. Right? You cannot escape lah. Wherever you go, you cannot escape radon or thoron. That is my master research lah. Radon or thoron gas. I cannot escape except where you live above the ocean. No? Then the radon or thoron will be coming from the land, no? But very little. Okay, you can draw your own mind map to summarize what we have studied. Right? What is the nucleus? What is the size of the nucleus? What is N? Okay, so this is your summarize all the facts. So basically, you are just memorizing facts. Okay, let's try some question.
Teacher,
Yeah,
my sem my semester test is like next week Monday, so would you recommend like do topic by topic or the whole paper for revision PYQ?
it's better to do topic by topic lah, because you won't have time to cover everything already. Only review through all that you have studied, and then if you still have time, try the past year paper topic by topic lor, area that you are weak in. No?
Oh, I cannot just like do 10 past year questions, like the whole paper.
Whole paper you have not learned waves yet lah. Can lah, if you want to, you can try lah.
Or
You
no,
can try.
excluding certain chapters, like superposition and waves.
You can try lah. It's up to you lah. But topic by
Oh,
topic will be better lor, because topic by topic give you a variety of question lah to try out. So
true, but
if you can do a few of them, then you're okay lah. You're ready lah. Then do topic that you cannot do lor. So
topic by topic, not much time already though.
a lot of question lah. The one I send you, you can see there. A lot of question.
Yeah, not much time already. Oh.
Not much time already. Fundamental particles, you have a lot to remember.
Oh,
So go into areas that you are not sure of. Lor.
for the semester exam, do the teachers tend to repeat from the past year? Like,
Usually we use past year question.
oh, so I can just do like 10 past year questions, past year paper.
Sometimes you may be lucky, you may find the question that you do come out lah. Because we
Okay.
use past year question from different years. There are so many papers, so it's unlikely that you will come across the same question lah. So you don't want any class next week lah.
Huh?
You want any class next week?
Uh, I think no need.
Next week take a break lor.
Next week take a
Then
break.
after that you decide whether you want to carry on or you want to take a break also lah. You
Uh,
contact me lah.
after next week, we should continue.
You contact me lah. What you want me to teach you lah?
Okay.
Okay, you should be able to write this one. Write an equation for the alpha decay of polonium to lead. Can?
Uh,
Should be able to write that.
transport. Yeah.
Then carbon 12 is stable isotope of carbon. Write the equation for beta minus decay of carbon 14 to nitrogen. Beta minus, you should be able to write the equation. Can? That is your answer.
Wait. Okay.
Okay, what is the answer for this one? Number 15.
I think it's C.
C, is it?
Ah.
No. This one goes straight through if it's far away. We are told two alpha particles with equal energy are fired towards the nucleus of both atoms. Which diagram represent the path? Right? It cannot be A, it is B. It is nearer here, the forces is stronger, so it's deflected more. Further away, the deflection is less. Okay? Uh,
Okay.
too fast. Sorry. Okay,
Okay.
the next one you should be able to do it yourself. Should be able to write the equation and then draw it on a diagram. This is a series decay lah, if you like. You don't need to memorize it, but you should use what you have learned to draw it up. So uranium 238 is here, given to you. And then it's 92. Alpha decay, alpha 4 nucleon, decreased by 4. And then the proton number decreased by 2. Okay? We should be able to write the equation. So it should go that way. To thorium. Thorium decay by beta minus to proactinium. On the diagram, show the beta decay by labeling the position of proactinium as Pa. right? Beta minus your A is constant, the Z increase by 1. Right? So that's your PA. Then you're asked to complete. The next one is alpha again. Okay, so that's your diagram. Tutorial. Okay or not?
Uh,
Anything not clear or anything you want me to explain? This alpha, your A decreases by 4, decreases by 4. Your Z decreases by 2. Right?
increases by 2.
The Z decreases by 2 from 92 to 90. Okay? Alternatively, you can
Oh,
write out the equation. 90, 234. For beta minus, your A is constant. A is constant. Your Z increase by 1. Z increase by 1. Okay or not?
okay.
Okay, I can proceed.
Yeah.
Okay, I don't think we will spend too much time on that. We can try the rest during the break time. This one I want to try with you. A radioactive atom decay by successive transformation to another isotope of itself. Which one of the following combination of particles could emit during the transformation? What is an isotope? First, you must know what is an isotope.
Oh, uh,
Can remember?
actually forgot the definition.
It has the same Z, same number of proton, but different number of A on neutron. Okay, we got 10 minutes time.
Same exact but different A, is it?
Same Z, different A or different N. N is number of neutron. So one alpha and one beta, no, cannot be. Because one beta minus will increase it by 1 only. Whereas one alpha will decrease it by 4. Right? One alpha decrease A by 4, Z by 2. So you want the same Z, the same Z. So you have to increase this one by 2. So each beta minus decay, the Z increase by 1. So answer is C. Can see the reasoning. Anything that is not clear?
Oh yeah, okay.
Okay, I think okay, the rest you can try yourself. Let me just make a start. Remember, you'll be cut off at any time.
Uh,
Okay, 11.2 fundamental particles. You just try the question, and then you don't know, ask me. Page 231, 281, sorry. Right, that's the syllabus. If you've got time, you can refer to that. Right? I did sell textbook reference if you want interested to read more. Okay. That's called the standard model of elementary particle. After a century in which scientists rapidly discovered many subatomic particles, subatomic means it's below the atom lah, they have developed a theory for how these come together to build up the material we see around us. The theory is known as the standard model. As the idea of atom as indivisible was swept aside by Rutherford and Thomson, right? Previously, people believed that atom is the smallest indivisible particle. So Rutherford and Thomson shows that no, there are other things smaller than the atom. So the idea of proton, so previously they thought proton and neutron are fundamental particle, but then they realized no, they are still smaller things in the proton and neutron. We have probed into the two nucleons, that is proton and neutron, and discover that each is constructed from a smaller particle known as quarks. Right? We use electron because electron is smaller than neutron or proton. Right? So we know that there's something inside there called quarks. The electron has so far survived as being considered fundamental. So electron is still the elementary particle or fundamental particle because there's nothing smaller to send into the electron. Nothing there. However, it has two partners, particles of similar type, each with neutrino associated with it, forming a group of 6 fundamental particles known as leptons. These are leptons. This is the electron, right? This neutrino. These are basically, if you like, can think of electron also, heavier electron. Scientists like to see universe as balanced or symmetrical, and we have now found quarks are also grouped in 6. These are your quarks. Purple one, group of 6. This is also group of 6. Don't worry about the red one. We won't bother about that now in the syllabus. Although only the lightest two are found in proton and neutron, these two. Lightest one is heavier. We call it different generation. So these two are found in proton and neutron. The heavy quarks are found in more exotic particle. These quarks are found in exotic particle. The two groups are distinct because quarks can undergo interaction via strong nuclear forces, whereas leptons do not feel the strong nuclear forces. Right? So quarks interact with each other with strong nuclear force. Right? So you won't bother about this part, not in our syllabus. It's the strong nuclear force that binds nucleons together, that hold the nucleon together. Each group of 6, there are 3 pairs with similar order of magnitude for mass, and also known as 3 generation. This is 1 generation, this is 2nd generation, this is 3rd generation. Okay, that's your size. This is cm, right? -8, nucleus is -12, proton is -13. I don't think you need to worry about all these sizes, only nucleus and atom. Right? Some call it elementary particle, some call it fundamental particle. Subatomic particles are particles smaller than the atom. Particles that cannot be broken down into smaller pieces. That's what it means by fundamental particle. Neutrons and protons are not elementary particles. Quarks, electrons, and neutrinos are elementary particles. Particles and antiparticle, matter and antimatter. Each particle has an antiparticle. Particle, example, proton, neutron, electron, neutrino. particle, example, electron, antiparticle, positron, positive electron. Not found in matter. Where do we find it? How do we get it? High energy collision experiment. That means it's more artificial. Man has to accelerate the particle to high speed to collide. High energy collision experiment found in particle accelerators. The particles are accelerated to high speed and then they collide. Interaction of cosmic ray with air particles. Cosmic ray are charged particles. They are coming in at high speed, so they collide with air particles up in the upper atmosphere. So cosmic ray are high-speed charged particles from space. Radioactive decay also produced. Matter and antimatter. Right? You have uncharged hydrogen. Nucleus is one proton and then one electron. Anti-hydrogen, the nucleus is negatively charged. Same as a proton, but negatively charged. Instead of electron, it's a positron. Right? Matter, electron, negative charge, antimatter, positron, positive electron. Same as electron, same magnitude of charge. Okay, I think we will stop here lah, rather than being cut off.
Okay.
Here lah.
What should I do now?
Try the question.
Okay. Continuing from question 20 plus, right?
Try all the question if you have the time.
Okay.
Okay,